So often, in the history of science, we see the practitioners of a reductionistic theory attempt to apply the theory outside the scope of that theory's explanatory range. We can forgive the practitioner's impulse to extend a theory's applicability beyond its scope for the simple fact that the theory had been so successful in its respective domain. As we saw in the very first chapter on reductionism and in the chapter on phase transitions, reductionistic explanations are compelling in their applications to narrow slices of the universe because of computational reducibility. Examples of misapplication and overextension of scientific theory abound, but here we will focus only on dark matter and inflationary cosmology. The adherent of general relativity who believes that the theory applies to all levels of scale from the Planck scale to the galactic and supergalactic is making a catastrophic and unfounded assumption. If we try to apply general relativity beyond the scope of planetary systems to galactic scales, which is at least 500 billion times larger, then the theory should predict values such as the rotational velocities of stellar masses and how distant photons are refracted and distorted by the curvature of spacetime. But according to general relativity, the rotational velocities are too high given the amount of visible baryonic matter. There is overwhelming evidence that these rotational velocities are systemically too high, leading to the conclusion that there is vast amounts of dark matter that doesn't interact with normal baryonic matter, meaning that it doesn't have an electric charge or feel the weak and strong nuclear forces, but yet still exerts a gravitational force on baryonic matter. Fritz Zwicky discovered this discrepancy between theory and observations in the early 1930s and coined the term dark matter for this hypothetical substance. Since the 1970s, experimental searches for this dark matter substance has failed. The following is a brief summary of dark matter candidates and their experimental failures. Massive compact halo objects, or MACOs, are assumed to be ordinary, baryonic astrophysical objects, such as brown dwarfs, rogue planets, stellar remnants, white dwarfs, neutron stars, black holes, populating galactic halos. These MACOs were attractive because they required no new physics. Years of gravitational microlensing surveys such as MACSHO, EROS, and OGLE ruled them out. Weakly interacting massive particles, or WIMPs, are hypothetical particles with masses on the order of 10 giga-electron-volts to 10 tera-electron-volts, interacting via weak force scale couplings. Strongly motivated by supersymmetry via the neutralino. Experiments such as Xenon 1T, LUX, PANDEX, Super-CDMS have not produced statistically significant detections after decades of searching. Axions are very light pseudoscalar particles arising from the Pecai-Quinn solution to the strong CP problem. Thus, axions were compelling because they could have solved two problems at once. Haloscopes such as ADMX and Haystack and helioscopes such as CAST have ruled out large swaths of coupling mass space. Sterile neutrinos are right-handed neutrinos interacting only gravitationally and via mixing with active neutrinos, even though the standard model had assumed neutrinos were massless. X-ray searches for decay lines, e.g. 3.5 keV line, remain controversial and unconfirmed. The gravitational effects are strongly limited by galaxy formation and Lyman alpha forest data that probes the matter density. Primordial black holes are black holes formed in the early universe from density fluctuations, not stellar collapse. Decades of microlensing searches proved them to extremely unlikely. Self-interacting dark matter is dark matter with strong self-interactions but weak interactions with baryons. Galaxy cluster collisions, e.g. bullet cluster, showed that overfitting from fine-tuning occurred when attempting to satisfy both galaxy data and dwarf galaxy data. Modified gravity theories, such as modified Newtonian dynamics or tensor vector scalar gravity, spectacularly fits galaxy rotation curves, but doesn't explain gravitational lensing and still requires dark matter in relativistic formulations, such as tensor vector scalar gravity. Superfluid, dark matter is dark matter that condenses into a superfluid phase at galactic scales, reproducing MOND-like behavior, but requires highly specific conditions to form the superfluid phase. No observational evidence exists. This is mainly a theoretical proposition. If we consider this decades-long lack of evidence through the lens of strong emergence, it is evident that general relativity can't be applied to the quantum realm, nor to the galactic and supergalactic scales as it is currently formulated. If our theory of strong emergence holds, then general relativity only exists at the planetary and subgalactic scale, and completely different theories are required to explain behavior at the other scales. For example, inflationary cosmology is another instance in which a planetary scale theory, general relativity, is misapplied at the Planck and quantum scale,